Okay, so for worked example 2, we have two new proofs to embark on, the sine of a subtract b and the cosine of a subtract b. Now, we've already derived the additive compound angle identities for a plus b for sine and cosine, but this result didn't appear in the diagram that we looked at. So we might need another approach to do these. So what I'd like you to do is to try and do this yourself first. So can you please pause the video and have a go perhaps on a separate piece of paper before we go through the proofs together. So please pause the video now. Okay, and let's have a look at the proofs. So what I've done here is I've added one of the latest additions to our toolbox, which is the sine of a plus b identity. And you'll notice there is a subtle difference between this identity, which we've already derived, and what we have to prove. And it's the sign change, isn't it? So we notice that there is a sign change here, and another sign change manifests itself on the right-hand side. So the question is, how do we show this, all else being the same? Well, we could do this with a straight substitution. And if I make a substitution, I can sort out the left-hand side immediately. So let's say let b be equal to negative b. Okay, that means that on the left-hand side, I'm going to have inside those brackets a plus negative b, which of course, with the positive and negative signs adjacent to each other, becomes a negative. So that means the left-hand side will read sine of a subtract b. So the question is, how does that play out on the right-hand side? Well, the best way to do this is to actually make the substitution. Okay, so therefore, we take the sine of a, and I'm going to be really careful here. I'm going to use a different color, and I'm going to substitute in probably with brackets as well. So we're going to have a plus negative b, like that. That's going to be on the left-hand side. And if I substitute negative b in instead of b on the right-hand side, we're going to get this. So we're going to have the sine of a multiplied by the cosine of negative b. Okay. And then add the cosine of a and multiplied by the sine again of negative b, like that. So the question is, on the right hand side, how do we get from the cosine of negative b here, the sine of negative b here, and the only resulting change being this positive becoming the negative that we can see clearly in 2a that's given to us. So we're going to explore that in a second. First of all, let's just clear up the left-hand side. So we can write that as the sine. I'm going to go back to blue again, I think. So therefore, we've got the sine of a subtract b because we're adding a negative. That's fine. So that's dealt with. Now, on the right-hand side, what can we do here? Well, we're going to do a bit of an investigation into the cosine of negative b and the sine of negative b. And we're going to do this using a cast diagram. And I'm hoping I can convince you that the result is correct in the proof. So for the cast diagram, I'm just going to draw it over here, like so. So we've got the cosine, all the sine, and the tan quadrants. And we're going to consider an angle B. So let's just say, let the angle B, as in the same B that we're interested in this question, be an acute angle. All right. Okay. Now I'm going to add B to my first quadrant. So I'm going to make this angle B with the horizontal. Now, in terms of reading off the angles, let's assume it doesn't matter, but let's assume we're talking about degrees here. If I go anti-clockwise, I'm going in the positive direction, which means that when I get to this point here, I've gone b degrees, okay, from 0. Okay, I hope we can all agree on that. And b is somewhere between 0 and 90 degrees. But what I can also do on a cast diagram is I can go in the opposite direction. Okay, so I'm going to add my angle B in the cosine quadrant C. Now, if I do that, you can answer this yourself in your head. If I'm going that direction, I must have gone negative B degrees that way. Okay, because I'm using my horizontal as my 0. I hope that's clear. Now, this idea throws up some interesting consequences. What if I take some trig values of these angles? Well, let's consider first of all what the sine of B is going to be first. So from the diagram, we can see that the sine of B, which I'm going to use that green color again, it's quite nice. So the sine of B, well, is it going to be equal to the sine of minus B, or negative B, perhaps? Is that true? Is this a true statement? Well, like I said in previous lessons, if we take the absolute value, as in we ignore the signs, then yes, this would be true. They would give you the same numerical value on the calculator if you ignore the signs, of course, whether it's positive or negative. But because we're dealing with trig functions and they have a periodic behavior, we know that all trig functions are positive in the A quadrants, okay? So the sine of B, as it stands, is a positive number, okay? Conversely, if we look at negative B, the angle I've just read off earlier here, that's in the cosine quadrant, and we know that only cosine is negative. I beg your pardon, let me say that again. That was a really important mistake that I just made. Only cosine is positive, okay, in that quadrant, which means that the sine of negative B cannot be positive because only cosine is allowed to be positive. So this is a negative number. If I want to make them equal, the only way I can do that is by sticking either a negative sign here or putting a negative sign here. Either way, we'll have a true statement. So let's see what the ramifications of this are now. Well, if I go back to my first idea, so if I take the negative sign off, I'm going to put the negative sign here, and I'm going to call that my first result. Okay, so I'm going to make this result look really important. So this is a true statement now. So I'm going to, again, like I said, I'm going to make this look important. Let's put it in, let's highlight it perhaps. So we tend to do in these videos, a lot of highlighting, but it does look nice, doesn't it? Okay, so that's my first result. So we now know that the sine of negative B is equal to the negative sine of B. Let's apply the same trick. Well, it's not a trick, but let's apply the same result to cosine. So what if I take the cosine of my angle B? So cosine of B, again, I'll use the green again. Is this equal to the cosine of negative B? What do we think? Well, let's go back through the argument again. Is this an equality? Well, in terms of absolute values, ignoring the signs, yes, always. But we know that the cosine of B is always going to be positive. That's just a fact. And if we look at the cast diagram, we also know that negative B is in the C quadrant where cosine is positive. So this is also positive. which means yes, they are equal. So this is a true statement. So the cosine of b is equal to the cosine of negative b. And I stipulated earlier that we said b had to be an acute angle. But I'll leave it up to you. If you wanted to do some further analysis using the graphs of sine and cosine, you'll see that these are identities and they hold for all angles. Okay, but I think I've made my point here. So we now have two results we can use, which I'm just going to make a note of. Okay, so we know that the sine of negative b is identical to the sine of b, and the cosine of negative b is identical to the cosine of b. And I've just noticed my mistake. I'm sorry. Negative there. So interestingly, if we consider these functions, because cosine of negative b is identical to the cosine of b, this is what we call an even function. So cosine is an even function because it's symmetrical about the y-axis. Sine, conversely, is what we call an odd function. Okay, it has rotational symmetry about the x-axis, the y-axis, sorry. About the origin, I should say, but no reflective symmetry. Okay, so that's just something about even and odd functions there. So cosine is an even function, sine is an odd function, but that's a little bit beyond what we're doing on this course. So let's use these results here now. So we can substitute them in. So we can now say that sine of a, and we can replace now the cosine of negative b, which is given here. We can replace this with cos b because we know they are the same. So I'm just going to put that in. Okay, and for the rest of it, we're going to add the cos a. And we also know that the sine of negative b here is the same as negative sine b. So I'm going to have to use a bracket here for this. So that's going to be negative sine of b, like that. And one more step and we're there. So I'm sorry if this is a bit convoluted. I just want you to understand the principles going on here. So the sine of a, cosine of b, and then I can bring that negative out to the front, subtract the cosine of a and the sine of b. Okay. So that's part A. Now, we're not going to go into that much depth with parts B because it's exactly the same principle. Okay, so part B, same substitutions, and we'll see that the cosine of A subtract B is exactly what it says there. So we'll just write it out. So part B, same process. The cosine of A subtract B. Well, in fact, let's undo that. It's actually going to be the cosine of A plus negative B. Okay, and that's going to be identical to the cosine of A multiplied by the cosine of negative B. Okay, subtract I'm using the A plus B formula for cosine. Sine of A multiplied by the sine of negative B. So yes, I've not written it out. If you are interested in the identity, I'll just put it on the screen again. You've seen it a couple of times. So the cosine of A plus B. So I didn't write it out first, which I probably should have done. Remember, is cos A, cos B, subtract sine A, sine B. So I've just used that fact over here. So sorry for skipping a step. Once again, we can just use that those substitutions that we found from the cast diagram. So cos of negative B is just the same as cos B, and the sine of negative B is a negative. So this is good. So I think we're going to get our result. So this is just going to be cos A. And remember, we can swap this for cos B. They are the same. Right there. And for the second part, we've got negative or subtract sine A. And then we replace all that with negative sine B. And we have the double negatives. Now, that's why we get the positive in that second identity. So we have the double negative there. So we're fully entitled now to write down the final step. So this is going to give us cos of A, cos of B, plus sine A, sine B, as required. For worked example 3, we have a show that, and as you can see on the left hand side, we've got some information here that we can use in a substitution using our new compound angle identities. So let's just write up that identity that we're going to use. So we know that the sine of A plus B is absolutely identical to sine A cos B plus cos A sine B. Right. So it's apparent that's what we're going to be using. The right-hand side is the consequence of having made these substitutions. So we'll deal with that later. So how do we get from this left side to the right side? Well, we have to decide what our A and B are going to be. So let's do that now. So it looks like we can say let A be equal to X, okay, which comes first inside the brackets, and B is going to be pi over 4, and obviously this is going to be in radians, isn't it? So let's substitute them in. And just make a note of what we're doing. So we're going to sub into the identity. All right. And if we do that, let's see what happens. So we'll sub A and B as X and pi over 4 across the whole thing. So therefore, again, the left-hand side is dealt with, isn't it? So that's going to be X add pi over 4. Just a straight swap for those A and B. No problems there. A is X, and of course B is pi over 4. Everything's positive, so nothing to worry about there. Let's see what happens now on the right-hand side. So this is going to be identical to, or equal to, sorry, I just realized that should be equal to because we've subbed in specific values. Okay, it's now an equation. So we now have sine of X. Let's put my substitutions in green here. Multiplied by the cosine of pi over 4. Okay, and add that to the cosine of X multiplied by the sine of pi over 4. And I'll just do that in green again so I'm consistent. So you might have an idea what's going to happen here. We're going to have to evaluate the cos of pi over 4 and the sine of pi over 4. Now, pi over 4, if you prefer working in degrees, is of course 45 degrees. It's a standard angle, so if you want, you can also use a little diagram, which I'm going to use up here. So for the sines and cosines, we'll do this in radians, of course. It's 45 degrees, which makes this isosceles. So it's an isosceles right triangle. This angle is, of course, pi over 4. So is the other angle, but it doesn't really matter. We only need one of them for this exercise. And then if we call the hypotenuse, beg your pardon, if we call the two shorter sides, because they're equal, they're going to be 1 and 1. Pythagoras' theorem tells us that the hypotenuse is, of course, going to be root 2. Yep, so we can see clearly from this diagram that the cosine of pi over 4 is, of course, 1 over root 2. And the sine of pi over 4 is equal to the same thing, 1 over root 2. But that's standard stuff. I mean, you'll know that from previously. So we just have to substitute these things in. So this is going to be the sine of x multiplied by, put those numbers in, so cos of pi over 4, 1 over root 2. And then we're going to add cosine of x, and we're going to multiply that by the same value. Now, this is where we can start to show that the right-hand side is indeed the same constant multiplying the sum of sine x plus cos x. So I can now factor out the 1 over root 2 to the front of this, and we can just leave the sine x plus cos x inside the brackets as required. So we can see clearly from this that the constant a is 1 over root 2, which you can rationalize as root 2 over 2 if you prefer. Okay, so that's just one use, or another use of these identities is to break down the sign of some kind of addition between two angles, one known, one not known, and you can make what we call a harmonic relationship where you have sine x and cos x added together. Now, for example 4, we have an expression where we've got angles 37 and 12, and we've got products of two cosines added to the products of two sines, and we have to write it as a single cosine. Now, this is a bit of Sherlock Holmes work here, isn't it? What clues are we given here? Well, what I've done is your go-to step would be to go to the formula book if you don't know these identities and just look them up. So I've just written both the sine in its two variants for the compound angle identity and the cosine one. So first of all, if you're sort of pondering which one to use, it's pretty clear because it says a single cosine, we can just disregard the sine one completely because that's just not going to be relevant. We're going to focus purely on this identity here. Now, when I say this identity, it's of course a combination of two identities. The a plus b and the a subtract b. So once again, what clues do we have? Well, if you look at the first two terms of this expression and the second two terms, they're separated by an addition, aren't they? Okay. Now, if we go over to the identities that we've whittled down, we've got the two cosine identities here, and we look at the sign in the middle. If the sign is going to be positive, then I need the cosine of a subtract b for this. So I'm just going to write out the identity that I'm going to use. So we're going to need the cosine of a subtract b because that's the identity that has the addition in the middle, which is what we need. So it's going to be the cosine of a cosine of B, add the sine A and the sine of B, which we proved in the first worked example as well. So we're getting warmer, we're getting closer. Now we can identify hopefully what A and B are going to be. So what is the repeat pattern in this? Well, we've got cosine of 37 and the cosine of 12, okay, in that order, which would correspond to the cosine of A and the cosine of B. So we can now deduce. So therefore, A is going to be equal to the 37 degrees, and the B is going to be equal to the 12 degrees. And you can just verify that with the sine part of it. We've got sine of 37 and the sine of 12, which of course A would be 37 and B would be 12. So we've got that information. That's the vital step, okay? Now we know what A and B are. We can use our identity now. So this expression has a single cosine equivalent. So let's just write out what we've just discovered. So the cosine of 37 degrees multiplied by the cosine of 12 degrees added to the sine of 37 degrees and the sine of 12 degrees multiplied together is simply the same as the cosine of A subtract B, which is of course 37 degrees subtract 12 degrees. There's nothing more to it than that, really. Okay, except that we can actually perform that subtraction, can't we? Okay, so this is just going to be the cosine of 25 degrees. Now, we don't need to evaluate that, okay? We're asked to write the answer as a single cosine. That's what it says there. And this is what we have here. Okay, so we've finished. Okay, so in example 5, we're going to see another application of these identities. And it tells us in the question to use the cosine of A plus B identity. So it'd be a good idea just to write that out before we begin anything. So we'll just do that. So we've been working with this for a while now. So the cosine of A plus B, and it's given to you in the formula booklet, of course, is the cosine of A multiplied by the cosine of B. And then remember, it's the sine, alternative sign, isn't it? It's subtract the sine of A and the sine of B. Okay, so we step back and think, what do we need to do here? Well, we are trying to evaluate the cosine of 105 degrees. Well, this is 105 degrees. That means that in my identity, the sum of A plus B must equal 105. Let's write that down. So therefore, A plus B must be equal to 105 degrees. We don't have any more information than that. It's just a case of what are A and B, or what could they be? Do we have options? Well, it looks like if we can write our answer down as some kind of real number, irrational though it may be, are there some cosine values that we know of angles that would actually sum to 105? And you were asked to do this in the warm-up activity. You were asked to find sums of angles that you are familiar with that would actually add up to 105. So let's think of what the A and B could actually be. Well, let's try A is equal to 60, because we know what the cosine and sine of 60 is. That's really handy. And B, to make 105, would have to be 45. Okay, so that's why I was asking for combinations of those familiar angles, 60, 45, 30. There's only a few that we deal with on a regular basis, and 90, of course. But 60, 30, and 45 are absolutely key, and they're just worth jotting down. These are the main angles that you will be dealing with in questions like this. Okay, and combinations of them. So consequently, you'll be looking for angles such as 105, which you've just seen is the sum of those of these two. Okay, but you could also look at the difference. So something like 15 degrees, we could also work with that. So there's a few alternatives, but just be cognizant of 30, 45, and 60, because those are the standard sines and cosines, and combinations of those now, because we can use these identities. Okay, so now we've established what A and B could be, we can go ahead and complete the question. And just as a reminder, if you want to know the cosines and the sines of all these angles, good idea is to memorize the two standard triangles. Good opportunity to revise this. So I'm going to draw the two standard triangles now and just give you a quick way of memorizing these. So first thing I would do, if we start off with the 60 and the 30 triangle, label those as 1, 2, like that. And a bit of Pythagoras, that's all you need to remember, would give root 3 here. And if you use a bit of common sense, if you notice that the lower side is obviously wider than, or the horizontal shorter side is longer than the vertical shorter side, that means that you're going to have the larger angle at the top apex. Okay, so this must be 60 and this must be 30. Just using a bit of deduction there. Okay, on the right-hand triangle, this is the 45-degree triangle. Put the angle on straight away. And we've just seen that in the previous example, 45 degrees in both corners means that this is a right isosceles triangle. And if we put the sides on, if that's 1 and that's 1, then this must be root 2. Okay, we now know everything we need to know, and we can just finish off the question now. So the cosine of 105 degrees is going to be equal to the cosine of what we've just said. So 60 degrees added to 45 degrees. Like that. That's the first step. And that's the sort of breakthrough step, isn't it? Once you've established that, you're on your way then. So that really important step there. Okay, now we can use the identity. So this is going to be equal to the cosine of 60 degrees multiplied by the cosine of 45 degrees. And then I'm going to subtract the sine of 60 degrees and the sine of 45 degrees, the product there. Okay, so that's just straight from the identity. I was just reading it off in front of me. That's all I was doing. So let's have a look. Cosine of 60 is up first. What is this going to be? Well, if we look at the diagram over here, the cosine, well, that's going to be the adjacent side. That's the hypotenuse. It's a half, isn't it? If you didn't know that already, you've got a calculator to do this, but I find it more useful to use these written methods. So this is going to be 1/2. Let's put that in there. Okay. Next up, we've got the cosine of 45. That's what we've got to do next. So we move on to our second triangle. The cosine of 45, well, indistinguishable from the sine of 45, that's 1 over root 2. So this is going to be a product. So it's a half multiplied by 1 over root 2. I'll do this one in red, 1 over root 2. That's the cosine of 45. And then we're going to be subtracting the sine of 60. Well, the sine of 60, going back to that triangle from earlier, there's the opposite. There's the hypotenuse. That's √3/2. So let's put that in. So that's going to be √3. Sorry about that. √3/2 multiplied by sine of 45, which we've already said is going to be 1/√2 again. Okay, I hope that's all right. So now we have to collect, well, let's multiply these out and see if we can write them as a single fraction. But the hard work's done now. So we've now got 1/2√2 subtract √3/2√2. So the nice thing is we've got the same denominator, but it looks like we're going to need to rationalize our denominators here. Let's write them as a single fraction first. So we have 1 subtract √3/2√2. Going right back to the beginning of the course now, multiply the denominator by √2 and the numerator by √2, remembering to multiply the whole thing. Let's see if this is going to work. So in the numerator, we're going to have √2 multiplied by 1, which is just √2. The product of the two roots, of course, you just take the product of the values inside them and write it as a single surd. So that's going to be √6. So it's looking good so far. Okay, and then in the denominator, we've got, again, the product of two surds. We just take the product of the values inside the surds, which is going to give us √4. √4 is, of course, 2. So the denominator is going to be 2 multiplied by 2, which is 4. And there we have it, as required. So for our final example, which is example 6, and we've seen a lot of variations on how we can use these compound angle identities. We're going back to this cast work where we look at obtuse and reflex angles, and we take the sines and cosines of them. And it's a case of deducing whether we have positive values or negative values. Now, for this question, it's a good idea just to establish, first of all, what values we're actually going to need before we start. And what I mean is, if I just write down A, if we're finding the sine of A added to B, we know from the identity it's going to be sine A cos B added to cos A sine B. Now, what information have they given us? Well, we know what sine A is. That's given to us in the question right here. Notice it tells us that the this sine angle, I beg your pardon, this angle is a reflex angle in the cosine quadrant from 270 up to 360. We're also told, so the sine A is accounted for. We've got that. We know what that's going to be. We also know what cosine of B is as well. That's there. So we've got the first two components, if you like, and we know that's an acute angle. What we need to find is the cosine of A and the sine of B from this information. So this is where we use our cast diagram. Now, I'm going to draw the cast diagrams over here on the right-hand side. And we're going to also link up with the work we did on the right angle triangles. So just as a little aside here, let's assume, we'll do the hard bit first. Let's assume that A is acute, first of all. So we always do this. If we're given an angle, it doesn't matter what quadrant it's in. Assume it's acute first, so you can get the values, irrespective of their signs, correct, and then use the cast diagram to decide whether they're going to be positive or negative. Okay, so for A, if it's an acute angle, we'll label it. So we'll call this angle here A. Now, what do we know already? If it's an acute angle, it's not going to have that negative sign at the front of it. Okay, so it's going to be opposite over hypotenuse, which is going to be 8/17. And if you wonder where I'm getting this from, I'm just reading off from here. So you can ignore the negative. Okay, forget about that. There's no such thing as an acute angle which has a negative sine value or a negative cosine value or a negative tan value. It just doesn't happen. What we would really like to find, however, is this adjacent side here. Okay, what is the value of that? Well, we just use a simple bit of Pythagoras, don't we? So using Pythagoras, the adjacent side is just going to be the square root of 17 squared subtract 8 squared. And you'll see very quickly this is a Pythagorean triple. So if we take that, so if you want to, you can do this on your calculator. So if we just take the square root of 17 squared and we subtract 8 squared, just click out of that, and that's equal to 15. Yeah, it's a Pythagorean triple. Okay, let's write that down. So that's nice. I always anticipate that. It would be a mean question to bringing in complex surds and things like that. Look out for the triples. So this side here is worth 15, which is really good. Now, we're in a position now to state what the cosine of A as an acute angle is going to be. So therefore, the cosine of A, and I'm just sort of caveating that, A is an acute angle, so it's going to be 15/17. Okay, for A as an acute angle. Now we use the cast diagram, and we decide whether this is going to be 15/17 or negative 15/17. Okay, so let's just label a few things here. So we've got C, A, S, and T, like that. And let's decide which quadrant we're going to put our A in. Well, it's between 270 and 360. So if we start at 0, of course, 270 is here, and then you get back round to 360, so it's going back to 0. So you're going to put your angle in there. We're in the C quadrant. What does this tell us? Well, if it's in the C quadrant, it means that cosine is positive, which is really good. Well, it doesn't matter anyway. We just know that for a fact now. So let's just write our conclusion. So for A as an angle between 270 and 360, it's positive. The cosine of A is also positive, so that's 15/17. So we've got that. All right, now that's all the sort of aside work done. And I just want to be clear, sorry, when we're assuming A is acute up here, I'm just referring to this half of that working. I'm just going to partition that now so it's clear. And we know that the A we're going to use, the cosine of the A we're going to use is, of course, this one. This is where A is not acute. It's a reflex angle in the fourth quadrant. Good. Now, what else do we need? We need to know the sine of B. Okay, the sine of B. We've got the cosine of A. We can sub that in when we're ready. That's there. Wouldn't it be great if we could find out what the sine of B is? Well, the good news about B is that B is an acute angle already. Okay, so all we need to do is deal with the right angle triangle. So for B as an acute angle, which it is, we just have to find out what the sine of it is. So if we draw the right angle triangle again, different one this time for B, we'll label everything. We'll call this one B, this angle here. And we know the cosine of B is 12/13. So let's just add those values. That's adjacent over hypotenuse. And we're, again, this is a triple. I won't do the calculation. You can do it for yourself, but a bit of Pythagoras' theorem will reveal quickly that that must be 5. Okay, so if you add 144 and 25 together, you get 169, which is, of course, 13 squared. So it's another triple. No need to draw a cast diagram now. So therefore, the sine of B is going to equal the opposite over the hypotenuse, which is, of course, 5/13. So we can use that as well. Let's make that look really important. Okay, so we're now, after all that prep work, we're now ready to evaluate sine of A plus B properly. So we sub everything in now. So this is going to equal, because we're subbing in, it's not an identity anymore, sine of A, which is negative. So that's going to be -8/17. That's given above, multiplied by the cosine of B, again, which is given here. That's 12/13. Okay. And then we're going to add the cosine of A multiplied by the sine of B. So add the cosine of A, which is this one. I'm just putting it in a box now to make it look extra important. So that's going to be 15/17. And you're going to multiply that by the sine of B, which again is very important. Let's make it look really important. The sine of B, which is here, which is just a positive, so that's 5/13. Okay, and if you want to, you can just plug all that into your calculator. Which is, if you just check, -21/221. Okay, so that's the first part done. So we've now established what the sine of A plus B is. All right, now let's have a look at the sec of A subtract B now. So once again, we're putting together a lot of different ideas. So for part B, we know that sec of some angle theta is identical to, and we use that third letter rule, don't we? The third letter of our reciprocal trig function corresponds to what is the reciprocal of, which is, of course, cosine theta. And in this situation, our theta is going to be A subtract B, isn't it? So the theta here and the theta here are going to correspond to this. All right. So what we're indeed doing is we have to find the reciprocal of the cosine of A subtract B. Now, we have to write out the identity for A subtract B, which we're going to do. So this is going to be 1 over, and if we just, this is a result we found earlier, wasn't it? If we take that, that's going to be the cosine of A multiplied by the cosine of B added to, just remember the signs are opposite for the cosine. It's a little bit unusual, maybe not what you'd expect. And then sine of A and then the sine of B. Okay, so that's just subbing in the identity. So you'll be familiar with this from earlier. I've just done a substitution where those purple highlights are. So what do we need to know? Well, we need to know the cosine of A, the cosine of B. Well, let's just check. Do we know the cosine of A and the cosine of B? Yes, the cosine of A is here. I've just ticked that. The cosine of B is given to us in the question. We've got that. We need the sine of A, which we've been using already, and the sine of B. So we just need all the same ingredients, just combined together in a slightly different way. So no need to do any extra work. We just plug everything in. So this is going to be equal to now, because we're subbing in values, 1 over, and let's write everything in. The cosine of A. So first of all, that's 15 over 17. Okay, multiply that by the cosine of B. I'm just reading that off. That was given to us in the question. That's 12 over 13. Okay, and then we're going to add the sine of A, which is negative. So we've got to be careful here. Let's put that in a bracket. Negative 8 over 17. Like that. And we're multiplying that by sine B, which is, of course, 5 over 13. Like so. So once again, you could just put all that into your calculator in one step. So let's do that. So we've got, and you can check this, please, 221 over 140. Okay, and that concludes the lesson.